Hello students, welcome to fourth session of Ansys Fluent Learn from Home. In today's session, we are going to see the modeling and simulation of 2D heat transfer problems. So basically, we will try to cover two problems in this session, which will going to clear most of your doubts. Hello students, in today's session, we are going to see the problems on heat transfer through 2D fluid flow systems. So we will start with a problem. So basically we are going to see our first problem on mixing of hot and cold fluid. Consider first of all we will open the new design modeler. It will take some time. Okay. So first of all we will change our units to centimeter. After that we will select our XY plane and we will select a sketch. We will draw a sketch on it. Then we will change the viewing plane to normal and we'll go to sketching. We'll start drawing our profile. So let us start the line like this. This is our first line, second line, third is a vertical line, fourth is a horizontal line. Then this is our inclined line. Then from here we will draw one other thing. Let this line be normal, so it will show a sign of perpendicularity. Okay. Then this is a parallel line. I will undo this and we will go to line, escape, line. Will start our line again from here and it is parallel. Okay. Then we'll draw one parallel line to this line and from here we will draw one perpendicular line. Okay, this much extra section we can trim. Okay, we'll trim it later on. Okay, first of all we'll go to dimension. We'll specify this dimension. So let this a distance from the center of this line. Okay, general distance of this line from center, it be 1.5. Okay, and this total length, let it will be 3 centimeter. Here they are not coinciding. Okay, then we will go to constraint, coincide this point and this point. Okay, after that we will go to dimension. We will specify the angle. Let this angle, okay, let this angle be 210. That means it is 120 degree. Let this line angle, it will be 60 degree. Okay, so obviously this will be 120 degrees, so it will show as an error. Okay, 150, sorry. Okay, after that we'll go to modify, trim. We'll first of all trim these sections. Okay, after that again we'll go to dimension. Let this length be 2 centimeters and this length is again 2 centimeters. What is L7? Okay, L7 is 2 centimeters and that is 3. L2 is B3 is 3. Okay, so now we had got our profile. Okay, Okay, after that we are just left with the length. So we will define this length. Let it be 10 centimeter. Okay. Also this length, let it be 10 centimeter, and this length, let it be 20 centimeter. Okay, we have to define this also. It will be 20. Okay, so we had completed our profile. So we will go to create, concept, surfaces from sketch. We will select this, apply, and generate. Okay, so our surface is generated. Okay, so we will close the design modular. After that we will go to mesh, edit. We had to wait for a couple of seconds for the mesh window to get open. Okay, so mesh window has been open. Our model is being loaded here. It will take some time. Okay, so our model is attached. First of all, we will see what type of mesh we get from general setting. Okay, so this is a very bad quality mesh. Okay, we had to do a lot of work in meshing here. First of all, we will go to sizing. Uh, in sizing, we will change. Okay, we will go to quality and we will make it high quality. Then we will go to insert sizing. We will select the edges. Okay, so we will select here edge 1, 2, 3, 4, 5, 6. Okay, apply. So on these 6 edges, we want suppose 100 divisions each. Okay, after that, again mesh, insert, sizing, edge number 1, edge number 2, edge number 3, apply. Now we want this as let's say 30. Okay, after that we will go to face meshing, then apply this surface. Now we will see, we will generate the mesh and what type of mesh we get. It will just take a couple of seconds. So we have to wait. Okay, so this is again not a very good quality mesh. So we'll do one thing, we will change the method. We will go to insert, method, then on this geometry, and let it be triangle, means all the meshing will be done by triangles. So let's check how is the quality of mesh now. Okay, so it's a good mesh now, but still I think here the size of elements are bigger, so it will going to affect our solution. So now we will go to element size. The default size is 1.6 e to the power minus 2, that means 1.6 centimeter. We will try to change this to 0.005, that means 5 mm, and let's see how is the quality of mesh now. Okay, so a little bit quality has been improved. Okay, so I think that's fine, because if we play in meshing, so it will consume a lot of time. So it's a okay mesh. Okay, so we will proceed further. Now we'll select the edges. So we will, let's say this edge, we are going to define this edge as inlet cold water. Okay, then this edge we are going to define as inlet hot water, and that this will be the outlet for the mixed water. After After that we are going to select all these 6 edges, 1 2 3 4 5 6. Okay, and we will say this as wall dash pipe. Okay, so you can see in name selection, this is our cold water inlet, hot water inlet, this is our outlet, and this is our pipe wall. So we had done with the meshing part. We'll close the mesh. The next step is updating the mesh. So we have to update the mesh. We have to wait till a green tick appears. Okay, so our meshing part is done. Now then we will go to setup. We will open the Fluent setup. We will click on the double precision and select OK. So Fluent window will open. Now first of all, our meshing is being loaded here, so we have to wait for a couple of seconds. Okay, so our meshing has been uploaded. Then we'll go to general. Now see, in this case our model will be a study for model, but here you can say there will be effect of gravity. We can add the effect of gravity, so we'll apply this in y direction. Okay, and it will be in downward direction, so minus 9.81 meter per second square, that is a standard unit. Now negative sign here indicates the gravity is in downward direction. Okay, so once you set the gravity has been applied to the model. After that we will go to model. Here basically a heat transfer is going to take place between the two fluid, hot fluid and cold fluid. So we'll tick on the energy equation. Okay, we will apply the energy model. Then we'll go to the fluid model, and we will change it from laminar model to K epsilon model. Again, there are a number of models. There's a big theory behind this model, so you can Google it. Okay, I'm using the standard models, so we'll click on the OK. After that, so our modeling part is done. We had set the model. We'll go to material. Now the standard materials which we already seen are air and aluminium, but in this case we require the water. So we have to recall water from the library. So we'll go to here and we'll select this water. So copy here. Okay, so water is being added. Now the pipe material I'm going to select as aluminium. If you want, there are other material available in the libraries, so you can select from them also. Okay, after that we'll go to cell zone condition. Now this body surface means this green surface. Okay, so which type of fluid here you want? You want a fluid, but by default that fluid is air. So here we are supposed to go in edit, and we are supposed to change it from air to liquid water and then apply OK. After that we'll go to boundary condition. You can see the boundaries which we had defined. Now our inlet cold. So our inlet cold is a velocity inlet. Okay, now see, in our last models there was only momentum. It was not showing the thermal, but here it is showing a thermal. Why? Because here energy model has been applied. If you click on the radiation, so this radiation will also appear. Okay, so our cold water is at 300 Kelvin, and we will define its velocity as 0.015. Why we are not taking 0.5? Because that is a high value of velocity. Mixing will not take place. Okay, so remember, for mixing we will assume that both the fluids are moving at lower velocity. Okay, similarly our inlet hot water, it is a velocity inlet. We will define its velocity as let 0.01 meter per second, and its temperature is now 400 Kelvin. Okay, after that our outlet is a pressure outlet, and our wall is our pipe is a pipe wall. Okay, it is wall. If you want, you can specify the roughness. If you want, let it 0.002 or 2 mm. Okay, so all our boundary condition we had applied. We will go to initializing the solution. We'll select the standard solution and initialize it from all zone, and then we will click the initialize. So initialization is done. Now we will go to calculation activity and we will set the animations, which animations we want to record. So first animation for pressure, so PRE pressure. Okay, first of all we are supposed to define the contour. Okay, so let it be for all these surfaces and pressure. Okay, so this is a initial pressure contour. Then we will select here and create the animation. Okay, then we will set the animation for velocity. So we will write here velocity, and we will go to new object contour, select here velocity. Okay, and it will be for all surface. Save and display. So this is our contour for velocity. Okay, after that next we will also apply one animation for temperature. Okay, we'll go to new object contour, select all the object, and from here we will select the temperature and save and display. Okay, so the temperature profile has been set. We will click to save and display, close, and then select contour 3 and OK. So you can see all the three animations have been set, and we'll go to run calculation, and we'll set some 250 iteration and do the calculation. So you can see this is our temperature animation of temperature is being generated. This is the animation of velocity. This is the animation of pressure which is being generated, and these are the residual calculation. Now it will take some time for the calculations to proceed. So I'm stopping or I'm pausing the video, and once the calculation are done, I will resume it. Okay, so our calculations are completed. The solution is converged after 136 iterations. Okay, you can see here 136 iterations, solution is converged. Okay, so we will close these tabs. Okay, and we will go to solution animation, and we will play back the animations. First of all, we will see for pressure. There is not much in pressure because the pressure is decreasing in the direction of flow. So you can see how the pressure is decreasing in the direction of flow when the flow is taking place. Okay. After that, the second animation is for velocity. Now, obviously, the velocity of cold fluid was 0.15, and for hot fluid it was 0.1. So obviously, the fluid which is coming from the upper pipe, it will have more velocity, so it is shown by red, and here they are shown by green. And after that, in this region the flow is accelerated. Okay, because actually combination of these two pipe, it is 2 centimeter and 2 centimeter, so 4 centimeter is the total diameter if we combine these two, and here diameter is 3 centimeter. So obviously the flow will accelerate because here the diameter is reducing. After that, the next is temperature profile. Okay, so we'll play the animation. So you can see how the mixing is taking place in this region. Okay, so you can see how the mixing is taking place between these two. Okay, so this is the final profile. Okay, so initially the mixing was very well, then slowly uh, the hot water is pushing this mixing area upward. Okay, so this is our final profile. We are going to see this in detail in our CFD post. So we'll close the print here. Okay, our solution is converged, so we are getting a green tick on the solution. We will open the CFD post, and we have to wait for a couple of seconds for the window to appear. Okay, so now we can see here our CFD post is open. first of all, there is no need to add the plane because it is a planar profile. Okay, so we will go to contour. We'll directly see this select the symmetry one. Now here what we want to analyze, first of all we want to see the pressure profile and let it be 100. Okay, apply. So you can see the variation of pressure, how the variation of pressure is taking place. Okay, here the pressure is more because the diameter is less. Here the diameter is more, so pressure decreases. Okay, actually combination of these two, it will become a 4 diameter pipe. Okay, remember this. After that, velocity, we'll see how the velocity variation is taking place. Okay, so already we had discussed here the value of velocity is 0.015 meter per second, and here it is 0.01 meter per second. Okay, so because of that, the more mixing is done, or the higher value of velocity is on the upper pipe, and here basically if you add this two, so the diameter will become 4 centimeter, and from 4 centimeter here the diameter is 3, so reduction is taking place, so flow is accelerated here. You can see this. Okay, after that the temperature profile. Okay, so we had already seen when the solution is converged. Okay, this is the region where the mixing of the fluid is taking place, and you can continuously see the temperature. Here the temperature was 400 degree Kelvin. Here the temperature has reduced somewhat. Okay, because this cold water is mixed in this region. Okay, after that, if you actually want to see what is the outlet temperature, so you can go to calculator. Okay, in calculator you can select this function calculator, and here we will say the average value, and what is which value we want the average temperature, and at what section, at outlet. So calculate, so you can see the average temperature at the outlet is 340 Kelvin. What was at the inlet cold? It was 300, which we had given. What was at the inlet hot? 400 Kelvin, which we had applied in the boundary condition, and at the outlet it is 340 Kelvin. Okay, so there is a drop in or rise in temperature of the outlet by 40 Kelvin. Okay, after that we will again go to our outline. Okay, so we had seen the contour. Okay, after that let us see the animation. So we will untick this contour. Okay, see, in contour only temperature, pressure and velocity, these are not the only properties. You can also see the other values also. For example, turbulence, eddy dissipation, you can see. Okay, suppose you want eddy viscosity. If that is a viscous fluid, it will show a good value. Sorry, eddy viscosity, so for turbulent flow. Okay, then other values are also there. What is the wall heat flux? Basically we are not supplying the external heat. Wall adjacent temperature, if you want to see. Okay, so there are also other values which you can see from here. What is the wall shear stress? Okay, no shearing is taking place here. Okay, so we'll untick this contour, then we'll go to streamlines. Okay, in streamline, obviously it is a 2D flow, so it will be a surface streamline. Now on which surface? On symmetry 2. Okay, and how many points? Let it be 50, or let it be 100. We'll see. Okay, we will try to see the animation. Okay, we will slow it down. So you can see basically actually here no slip condition is taking place, so this fluid particle is moving slowly. Okay, you can see actually our 100 is a more point, so we will reduce it to suppose 75. So in that case, that blue point, it will not appear. Now let's see the animation for 75 data points. Here again it is appearing. It is too slow. I have to increase the speed. Okay, now it is too fast. Between somewhere here. See, here the no slip condition is existing. So that's why that fluid particle is moving very slowly. Okay, so I think you had understood the physics behind this. See, basic physics is here 0.15 meter per 0.015 meter per second is the velocity. So here the fluid is moving fast. Here the inlet velocity is 0.01. So here the fluid is moving slow. Okay, and here the combination of these two has 4 centimeter area, and here the area of passage is 3 centimeter diameter. So here the fluid is accelerated. Okay, after that let us see how the pressure variation is taking place along the x-axis. So again we will go to location, line. We will try to insert a line. Let its y and z component be 0 because it is on the x-axis. We will say it from minus 0.2 to let's say 0.5. Okay, so it's a very big line. Let it be 0.02, and it be 0.4. We'll untick this streamline. Apply. 0.02 to 0.25. Okay, let it be 0.2. Let it be 0.01. So it is 0. Only. Okay. So we had got the approximate line along x-axis. So we'll go to, and here we will divide it into 100 samples. Okay. Now we will go to chart. We'll insert the chart. Again data series. We will select the location as line 1. After that, on x-axis chart count, which is 100. On y-axis, if you want to plot for pressure, so you can see this is a plot for pressure. Okay, if you want to plot for temperature, so you can see here temperature. Okay, so actually there is a turbulent mixing, so in this case you can see the temperature variation is continuously changed. Okay, if possible. Okay, then if you want to see the velocity, so you can see the velocity is accelerated. Okay, in the direction of flow. Okay, so again we'll untick this chart. Okay, we will see the streamline. Tick here. Apply. Okay. Now in the streamline we had seen for velocity, so likewise you can see the wall shear stress. So basically no shear stress is taking place here. Okay, so velocity. Okay, so in this way we had completed our first problem for today's session. Hope you might have enjoyed the today's problem. There is not much difference between the method of solving the problem of pure fluid flow and fluid flow with temperature. Only the difference is here you are supposed to set up the energy model in addition to the turbulent model. Okay, so now we will start with our second problem. So second problem we are going to take that will be flow over the cylinder in 2D flow. Okay, how is the formation of velocity as well as thermal boundary layer when the flow is taking place over the cylinder. So we'll start with fluid flow fluent. We'll select the geometry, right click, new design modular. It will take some time to open. Okay, after that we will change the units to centimeter. We will take the XY plane, create a sketch, and then normal to that sketch. Okay, and we'll go to sketching. First of all, we will draw one rectangle that will define our fluid path. Okay, after that dimension. So let this dimension be 10 centimeter, or let it okay, 10 centimeter. Let this entire length it be 50. Okay, after that let this distance it be again 10, and the entire height of this rectangle it will be 20. Okay, so this is our path of fluid flow. So that will go to concept, create sketches from create surface from sketch, and select the sketch, and we will generate. This will be our fluid path. Okay, after that again we will go to XY plane. We'll select this and we'll draw another sketch. Okay, after that we'll go to sketching. In sketching we will select a circle, let it be defined at the origin, and let its diameter be, let it be 3 centimeter. Okay, after that we will go to concept, sketches from surface from sketch, select the sketch. Now see, if you add the material, so basically one body will be there. Okay, I am generating it, so basically that circle merges with the body. Okay, so if I want it separate, so I had to go to edit selection, here convert it to add frozen. Okay, after that we'll generate it. So now you can see there are two bodies. This is a cylinder, we can rename it CYL for understanding, and this is our surface body, that means fluid paths. Okay, but right now they are overlapping with each other. Okay, that means if I hide the body, so the fluid path is a cylinder, a rectangle right now. So for that we had to do the boolean operation. So we will have subtract. Now our target body is fluid body, and our tool body is cylinder. Okay, and do you want to preserve it? Yes. Then we will, after that we will generate this boolean. Okay, so if I hide this cylinder, so you can see, okay, there is a hole now in the fluid body. Okay, so show all bodies. Okay. So now we had a completed our modeling, so we will close the design model. Then we will go to meshing. In meshing we will edit the mesh. It will take some couple of time, so we have to wait. Okay, so our meshing windows opens, but it is taking some time to attach the geometry. Okay, now so the geometry is now attached. Now first of all we will see by default setting what type of mesh we get. Okay, so it is a very poor mesh. Okay, first of all we will see the element size is 2.6 centimeter. We'll change to 5 mm. Okay, after that we will do one thing. We will insert sizing. We'll select edges, edge 1 and edge 2. apply, and we will divide it into 100 divisions. After that, again sizing, let this is h1, h2 and h3, apply, and we will divide it to, let's say, 50 divisions. Now let us update the mesh. I had to wait for some couple of seconds. Okay, so it is not that much good quality mesh. Okay, we will do one thing. We will try to insert the inflation. Now, what is inflation? Now, see, in inflation, basically this is an edge. Surrounding to this edge, there will be some layers in which very fine meshing will be done. Okay, so I'm selecting this edge. First of all, selecting the geometry. I want it on this geometry. Apply. Then select the boundary. I want this boundary. Okay, then how many layers? Suppose I want 10 layers. Okay, then we will see, we will update the mesh and see what happens with the mesh. And we had to wait for some 10-20 seconds. Okay, so let us see the mesh. Now you can see here there are a number of layers where very fine meshing is done, but still it is not a good quality mesh. So our last method is we will go to method and we'll change the method type. Select these two surface, apply, and I want all the elements to be triangle. So now we will update the mesh. Okay, now you can say it is a good quality mesh now. Okay, still there is a very large scope to update the mesh, but we had to work a lot for that. So again, meshing is not a part because there for a particular problem we can take a session of 1 or 2 hours for meshing. Okay, so we will skip this part now. It's a fine mesh, we can say it's okay, we will get a good solution. So we will go to select edges and we'll define our boundary condition. So let this boundary be our inlet. Okay, let this boundary be our outlet. Okay, after that let these two boundary uh, it is a wall, you can say it is a wall boundary, or we can say simply wall surface. It is a wall surface, and let this boundary, we will call this as cylinder. Okay, now we will see on name selections. So this is our inlet, outlet, wall surface and cylinder. Okay, so we will close the mesh. After that we are supposed to update the mesh. We had to wait till a green tick appears. Okay, so now our mesh is okay. We can right click on the setup and we can open the Fluent setup. So double click, click on the double precision and apply OK. So a Fluent window will open. Now our mesh is being recalled here. So it will take hardly 5 to 10 seconds because it is a 2D. In 3D problem, it requires some time. But in 2D problem, yeah, you can see the mesh has been uploaded. Okay. Then again, it is a steady state planar model. No need for transient. Here we will not apply gravity. Then in model, basically energy transfer or heat transfer will take place. We will apply the energy equation. Okay. After that, in viscous, uh, this is a flow model. So here we will select K epsilon turbulent model. Okay, and select OK. After that, we will go to material. Already air and aluminum. We are fine. Our fluid is a air fluid. We will say we are going to model for flow through air and let this cylinder, it is made up of aluminum. So no need to update the material library. Then in cell zone condition, you have to define that this cylinder, it is a solid. Okay, it is not a fluid. That solid is aluminum, or its material is aluminum. Then this surface body, that means this fluid body. Okay, it is a fluid, and its material, the type of fluid is air. So simply click OK. After that, we will go to boundary conditions. In boundary condition, let our inlet is a velocity inlet, and we will specify the value of velocity. Here the heat transfer is taking place, so we will keep the velocity somewhat low. Let it be 0.15 meter per second. Okay, and inlet air temperature, it is 300 Kelvin. Okay, after that, outlet is a pressure outlet, so nothing to change. Okay, after that, wall cylinder. Okay, so this wall cylinder, we can say on this wall cylinder the convection is taking place. Let's say its temperature is 400 Kelvin and heat transfer coefficient, I am giving bigger value, 20, so that we will get a good thermal boundary layer. Okay, and again this cylinder, okay, you can consider this cylinder also. Here convection is taking place. This value is 20 watt per meter square Kelvin, and let its temperature be 400 Kelvin. Okay, so we have set the boundary conditions, and this wall surface, that means these boundaries, you had nothing to do with that. Okay, so we will go to initialize the solution. We will have a standard initialization. Let it be from inlet, or you can select all zones. Then calculation activities, solution animation. We will have here 3 animation. First will be for pressure. Okay, so we will go to contour. We will select all these surfaces, save and display, and this animation. Okay, so this is a pressure animation. After that, second animation we will plot for velocity. Again, new contour, all the surface, and let it be velocity. Save and display. Okay, we forgot to select, okay, velocity. We forgot to select the contour. Apply OK. Okay, then third animation we will say it is for temperature, so TMP. Then we will go to new object, contour, select all the surfaces, here temperature, 7 display. Okay, after that we will go to run calculations, and we will apply some 250 iterations and start the calculation. So the calculation have been started. Now you can see this is a thermal boundary layer. Okay, how the thermal boundary layer is getting formed. Okay, this is a velocity boundary layer and this is a pressure control. Okay, so we had applied for 250 iteration, but I think we will get a converse solution. Almost the error are in 10 to the power minus 4. So we will somewhere around 100 iteration we will get the converse solution. Okay. See here it also showing the time. So at least 7 minutes will be required for getting the solution. So I am pausing the video and I'll resume it when the solution is converged. Okay, so we have completed our 250 calculations iterations, but actually we haven't got the converge solution. And seeing this curve, okay, you can see this curve, it is going up, going down. That means it is repeating itself. Okay, so actually the solution is not converged, but it is equivalent to converge solution. Okay, because the curve have become flat. Okay, so we can assume that it is a converge solution, because even if we do 1000 iterations, so this line will go horizontal. Okay, so we can say it is a converge solution. Now this is a thermal boundary layer, velocity boundary layer, pressure variation contour. So we will see their animations. Play back the animation. So first of all, we will uh, slow down the some. Okay, sorry. We will slow down some speed. Okay, and we will play the video. So this is a contour of pressure variation. Okay, now you can see here red region. So red indicates higher pressure. So basically here this is the point where the fluid is coming to rest. Okay, you know what is separation point, what is stagnation point. So this is a stagnation point where the fluid is at rest, and whatever the loss of kinetic energy, it is basically converted to increase the pressure. Okay, and you can see here there is a formation of boundary layer. So in this region basically the pressure is low. Okay, and this green region is nothing but our cylinder. Okay, I should increase the speed. Okay, so I think pressure control is understood to everyone. So we will see we'll play the video for the velocity control. So let us stop. Okay, now we will see how the velocity boundary layer is formed. Okay, so now you can see there is a formation of velocity boundary layer which is taking place. This is a wake region. This blue region, it is nothing but wake region. Okay, and this entire path is nothing but our velocity boundary layer. Okay, now what is velocity boundary layer? Everything, I think all second year, third year and final year students are attending, so they have learned everything in fluid mechanics. Okay, so this is the actual formation of boundary layer over the cylinder. After that we will see our next video, formation of thermal boundary layer. So thermal boundary layer second year students are not aware of, but they are going to learn in next semester heat transfer. Okay, and TB students already they are aware. So we'll play the animation. Okay, so you can see how the heat is being transferred. Okay, so this is our thermal boundary layer region. It is the region where the temperature variation is taking place. This air comes in contact with this hot cylinder. Because of that, some amount of air is heated, so the temperature gradient is uh, existing in this much path area. So this is nothing but a thermal boundary layer. Okay, so I'll stop the video. I think we will go to post CFD and we will further see the okay, so right click on the CFD post and we will edit the CFD post. We have to wait for some 10 seconds. Okay, So CFD post has opened now. Okay, so there is no need to add the plane again because it is a 2D planar surface. Okay, so we'll directly go to contour. We will make here let us say 100 contours. Okay, and okay, we will apply this for surface body. Okay, so this is the pressure variation. You can see this is a separation, this is a stagnation point, and here the boundary layer separation is taking place. Okay, so here negative pressure is there, so you can see here blue line indicates negative pressure, and this is a region where the pressure variation is more, and after that here the pressure almost again become constant. After that we will see the velocity profile. So velocity profile will give us the velocity boundary layer. Okay, again here the flowing fluid will come to rest, so pressure was more in this space. You can see this blue point here, the pressure was very high and the velocity is 0. Okay, after that this is a wake region where negative pressure is created. Okay, and this is a region where there is a continuously velocity gradient is taking place. So this is nothing but boundary layer. Okay, after that we will see the temperature profile. So we will get our thermal boundary layer. This is our thermal boundary layer. Okay, so this is a region where the temperature variation or temperature gradient exists. Okay, after that we will untick this contour and we will see the streamline of flow. Okay, so start from inlet and let it be inlet. So you can see how the streamlines, streamline along the direction of flow. Okay, so we will play one animation of this. Okay, so in this way the flow is taking place. Okay, hope you might have understood the physics behind the formation of boundary layer with the help of this video. Okay, after that if you want to plot the temperature variation or velocity variation along the line, so for that we will insert one line again. Okay, let the line be passing through. Okay, let the line be passing through x-axis. So y and z coordinates are 0. Here we will say minus 0.15. I think minus 10 centimeter, 15 centimeter is the distance on negative x-axis, and on positive x-axis 0.5. Apply. We'll untick this streamline. Okay, so the line actually it is I think 10 centimeter, 0.1. Okay, and here I think 40 centimeters, 0.4. Okay, now so let this line is divided into 100 samples. Okay, so now we can go to chart. Okay, in chart we are supposed to select this data series. Location will be line. Apply. Then we will go to chart count along x-axis is a chart count, and along y-axis it is, if we plot for pressure, so you can see basically before the cylinder, basically the pressure is constant, and at stagnation point the pressure abruptly increases and then wake region is formed. So in wake region the pressure is below atmosphere and then the pressure increases. Okay, if we talk about the velocity along this line, so you can see the velocity before the cylinder the fluid is retarding, okay, along the x-axis, and this space indicate the uh, cylinder region. So in cylinder was stationary, so no velocity flow. Before the cylinder, basically the velocity come to 0. You can see the 0. Okay, so this is stagnation point, and after that there is a wake region. So in the wake region, the velocity is very low. Okay, and as the thickness of velocity boundary layer was reducing, okay, so the velocity was increasing in the direction of flow. Similarly, we can see the temperature profile. Okay, so you can see at the cylinder the temperature was 400 Kelvin. So this thickness represents the cylinder temperature. Before that, the air was no heat transfer is taking place, so air is having 300 degree Kelvin. Here on the boundary, you can see on the boundary heat transfer is taking place, and before the uh, cylinder, the fluid came to rest. So at that point, the fluid has reached almost 400 degree Kelvin. So you can see this small line represents the thickness of thermal boundary layer, and here the temperature rises to up to 400 degree surface temperature. And after that, uh, in the thermal boundary layer region, the temperature is slowly dropping, and finally the exit temperature is somewhere around 310 or 308 degree Kelvin. Okay, we can also see what is the exit temperature. So I think this graph is understood. Okay, then we will go to calculator, function calculator. We will select here average. Okay, what we want the location will be outlet. We will select here temperature. Okay, what we want, one minute. We want temperature. Okay, then calculate. So you can see I think 301. Okay, so you can see the temperature has risen only by uh, 1 degree Kelvin. Okay, so inlet temperature was 300 Kelvin and outlet temperature is 301 Kelvin. Okay, this is because at around 45 centimeter, the thickness of thermal boundary layer has been reduced considerably small. Okay, so in this way we had completed today's session. So today we had taken two problems for two-dimensional heat transfer. Okay. In tomorrow's session, we will take some problems, one or two problems on three-dimensional heat flow. Okay, how to apply the energy equation, how to set the model for three-dimensional heat flow. Hope you might be enjoying the session, and I am assuming that you might be learning at home with the help of my sessions. So in this way, I end today's session. So stay safe and please take care of yourself and follow the social distancing. Okay, thank you for a patient listener.